Okay, so we are going to start looking through our material for our Math 180 pre-calculus class. Starting with Chapter 1, Section 1, we are looking at functions and function notation. So when we are looking through the kind of the beginning of this section, we're really going to define some terms that we need to be aware of and kind of be speaking the same language. So a relation is really any set of ordered pairs or any relationship between variables. So, any any equation between x and y, or even potentially a third variable as well, would be a relation or a relationship between variables. Um, when we talk about the domain in more of an elementary sense, we're referring to all the possible x values. Now, we may have different variables. We may be using s of t and t, or f of n and n. So we may be using different variables. So we don't want to just think about the x as the domain, but whatever our input is, whatever we're plugging into the function. This would also be the independent variable. And then our range then is all of the possible y values. Again, that's kind of the elementary way of thinking of it. This is the output. This is what you get out of your equation after plugging something in. So these are our outputs or our dependent variable. And then a function is a very special type of relation. So think of relation as kind of the broader term, and then a function is a specific type of relation where each member of the domain matches with only one member of the range. So if we're thinking about ordered pairs, there's no repeated x values matching with different y values. If we're thinking about a graph, this is something that passes the vertical line test. And so we'll be taking a deeper look in this section at what a function means. And then, like I just kind of went over above, our independent variable, most often x, but this is our input. It doesn't have to be x as our variable. It could be t, it could be some other variable that we use, but this is our input. And then our dependent variable, most commonly are y, but again, it doesn't have to be y. It could be f of x, it could be s of t, it could be some other function. This is our output. It depends on what the input is. And then f of x, hopefully you're familiar with seeing that. That is referred to as function notation. So what we're going to be doing in these first couple examples is looking at some sets of points and stating the domain and range, and then determining whether it is a function or not. Domain and range, when we are looking at a set of points, is usually written in what's called roster notation, where we're essentially listing off some numbers. So the domain is all of those inputs, 1, 2, 3, and 4. And then our range would be all of those outputs, our y values, 6, 6, 8, and 9. Just because I have 6 twice doesn't mean it needs to be listed twice. I do only need to list it one time. Now determining if this is a function or not. If you recall, each member of the domain matches to only one member of the range. Essentially, if we're looking at a list of points, we don't want our x values to repeat with different y values. So all of my x values here are unique. There's no repeated x value. This means that this is in fact a function. In fact, all of the y values could be 6 and it would still be a function. What we don't want is those inputs to be repeated. So we can go ahead and write that this is a function. And then we can go ahead and look at the next one. So in the next example, you can see I'm not terribly creative. I just switched all of those points. Let's go ahead and state our domain and our range. And these two functions are actually inverses of each other, which we'll get into later on in this chapter. But my inputs here are 6, 6 again, 8 and 9. I don't need to list 6 twice again. And I don't actually need that little parenthesis I put in here. And so we have our range now we can list 1, 2, 3, and 4. Those are the outputs we have there. And then determining whether it's a function or not. Again, like we said, each member of the domain, so 6 is a member of the domain, should match to only one member of the range. Well, 6 matches to 1, and 6 also matches to 2, which means this is not a function. All right, now looking at the next example, we have a graph here, and we're going to state the domain and range for the given graph. In this example, you're not being asked to graph, you just are interpreting what the domain and range is from the graph. Now, when we're stating domain and range, we are always listing things from least to greatest, or parentheses here. And so what we're going to be doing here is looking at my domain. And in this case, this would be the x-axis. So thinking from least to greatest. So as I think from least to greatest, this function continues to go like this forever and ever and ever and ever. And so thinking about this, we have from negative infinity, because these x values are all going to get hit as this keeps coming this way forever and ever and ever. I can't find what that first x value is. So my domain is coming from negative infinity and goes all the way. There's no interruption, there's no holes, there's no asymptotes, there's nothing that interrupts the x values being used here. And then the very last one would be 1. And notice it has a closed dot here. That means it does actually equal 1. So we will use a bracket on 1. Range is going to be looked at in the same way, but we're looking at the y-axis now. So thinking least to greatest. So starting down here, I have no y values at all, none, 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 until I get here to y equals 0. At y equals 0, my function actually touches the origin there, so it is including y equals 0. But that is my very first y value, and I will use a bracket on 0 as well because it does actually equal 0. And then we can see that my function continues to increase forever and ever and ever, and we will never reach that last y value. So it's going on to infinity. And we will use a parenthesis on infinity. Infinity always gets a parenthesis, both negative and positive. Now, sometimes I'll have students say, but wait, what about this side here? It stops here. Yes, it does. And I could list from 0 to 1 as well, but listing from 0 to 1 would be redundant. I would be essentially repeating what I have here. I already have from 0 to infinity. So if I already have 0 to infinity, listing also 0 to 1 is not really necessary. And moving on to the next example, we have another function where we are asked to find the domain and range. And your graph or your picture may not have these holes on here, but you can go ahead and draw a closed dot here and an open dot here. And we're going to state the domain and range again. So again, our domain is our inputs are, in this case, we'll assume x values. It's not labeled as x and y axis, but we can go ahead and make that assumption. Thinking least to greatest, this function does not go on forever. It stops here and stops here. So my very, very first x value being used is -4. And it is a closed dot here, so it does in fact equal -4. So I'll go ahead and use a bracket there. And then my x values continue without interruption. There's no holes, there's no asymptotes, no gaps, all the way until we get to +4, but it's an open dot there, so I will use a parenthesis. This notation we're using here is called interval notation. We'll see a little bit more detail about that in section 2. You can see here that I'm using these brackets and parentheses, but we'll see more examples of that as this chapter continues. Then the range, again, looking now at the y-axis, thinking least to greatest, we're looking all the way, no y values, and our very first y value here at -8. Well, it does in fact equal -8, it has a closed dot there, so I'll go ahead and use a bracket. And then my y values are not interrupted. Again, no holes, no asymptotes, no nothing, until we get here to +8. And then it stops. And we'll use a parenthesis because it has an open dot. So that's the domain and range for that graph. The next one looks a bit faded, so I'm just going to kind of give it a little bit more definition here. And you can see here that we have some closed dots, some open dots, and then this function continues down here forever. So if I'm stating my domain and my range, we can see that we have what's called a piecewise function. So this is where we have two different types of functions kind of put together on the same coordinate plane over different domains. So we're still thinking least to greatest. And as I think about my domain, there are no y values. It ends right here, or rather x values, no x values at all. My very first x value is here at -9. It has a closed dot, so it is defined there at -9. And then it has no interruptions. It goes continuously until we get to x equals 1. And it's an open dot there. So it is ending there. We'll have a parenthesis there. When you're listing multiple intervals, you're using this union notation here. It's essentially acting like a comma where we're listing multiple intervals here. So now we're going to go ahead and see, okay, well, it ends here, but then it picks up down here. Now, neither one of these are closed, so the function is not defined at 1. I can go ahead and use a parenthesis again from 1, and then it continues on, and this graph goes forever this way. Now, it's going very slowly to infinity, but it is continuing to go out further and further and further on to infinity. So I have from 1 all the way to positive infinity. Now, sometimes what students will say here is that they want to write that this is going down to negative infinity because your function is going down. Remember, we are not looking at the y values for our domain. For our domain, this is moving further towards positive infinity on the x-axis. We will consider that this is going down when we're looking at our range, but for the x values, as we're going from 1 to infinity here, we're going to positive infinity, even though the function is going down. Now for our range, this is where we'll kind of take the fact that this is going down into consideration. Again, I'm thinking least to greatest. So if I'm looking at from my lowest values down here all the way to my highest values down here, this is going down forever. I can't reach that last value. So we're coming from negative infinity and we keep coming up, we keep hitting all these y values. There's no holes, no asymptotes, but then we get to -3. And it stops there. And I'll use a parenthesis because this is an open dot. My function does not actually equal -3. And then we have a gap here from -3 all the way to y equals 0. Now, the next interval here, again, we're looking just at the y-axis. So my y value here is 0. My x value is -9, but my y value, what we're looking at here, the range, is 0. So then it continues on from 0, and I'm using a closed or a bracket here because it is a closed dot. It does actually equal 0. And then we hit every single y value all the way until we get to 5. And then we have an open dot there. It does not actually equal 5, so we'll use a parenthesis. So if we have multiple intervals or multiple pieces of a function, we can list multiple intervals here for our domain and range. Now, the next example, we've seen a set of points, we've seen a graph, and now we're going to look at an equation. So what we have here is a rational function where we have a square root in the denominator. So when I'm thinking about writing my domain, I need to think about everything that would make my function undefined. Well, if we're looking at a rational function, I know my denominator can't equal 0. So this 3 minus x cannot equal 0. The other thing I need to consider is that I can't take the square root of a negative number. So this 3 minus x needs to be greater than 0. Now, if this square root was in the numerator, it would be okay if it equaled 0. But because it's in the denominator, it cannot equal 0, so we won't put that equal to inequality there. Now, what this tells me is that x, if I add x to the other side, I know that x cannot equal 3. So 3 cannot equal x. And I can add x over, and I have 3 greater than x. Or if you'd prefer to see this as x less than 3, again, the small point to the x and the 3 is the bigger part of the inequality there. That tells us that x needs to be less than 3, but x cannot equal 3. Now, in the instructions here, it does not tell you to draw a number line, but it's actually a really helpful tool to visualize what you're looking at here. So if I plot some values here, I can go ahead and put 3 here. And we know that x cannot equal 3, so I'm going to put an open dot here. And then we know we want the x values that are less than 3. Okay, so less than 3 would be everything going this direction. And so if I want to state my domain, having this visual is really helpful. We're going from negative infinity all the way to 3. All right, so those are examples of looking at domain and range. What we're going to move into now is evaluating functions. So if I'm looking at this function here, I have f of x is equal to the same function that we had listed above. But here it's asking me to find f of negative 1. What that means is plugging this x value into my function. So f of negative 1 is equal to negative 5 times negative 1. And I'm going to plug that negative 1 everywhere I have an x. So it's going in for all of the x values. And then I have 3 minus negative 1. Well, a negative times a negative gives me a positive 5 up top. And underneath my square root here, I have 3, and that becomes 3 plus 1. And that's the square root of 4. And then the square root of 4 is 2. So f of negative 1 is 5/2. In that next example, we have now a table. Now, functions can be represented in 4 different ways. I probably should have mentioned this at the beginning of the video when we were going over the definitions, but I'll do it here. We can have functions represented as an equation or algebraically. We can have functions represented as a table or list of points, in other words, as data. And we can also have a function represented visually as a graph. The fourth representation of a function would be verbally or a word problem. So we're seeing 3 or 2 of those here. We're seeing it represented as a function, and now we're seeing it represented as data. I will, throughout this class, try to show you all 4 of those representations and tying them together. Sometimes we kind of divide math up of this section is about graphing and this section is about solving an equation. And really we're talking about the same material, but representing it in different ways. So hopefully this class will help to tie all of those together for you. Now finding f of negative 2, this is my x value. So I'm looking, well, where does x equal negative 2? And that would be this column right here. Well, my function's value at negative 2 is negative 4. So not a whole lot of work to show for these. Now, these next 2 problems are getting us set up for function composition. So this is where we have a function and we're plugging another equation into that function. So here I have to find f of 2a. Well, what that means is I'm going to take this function f of x, and what my recommendation to you is to always write out the function, replacing x with parentheses, and you're replacing all of the x's with parentheses. And then you want to plug in what you are trying to plug in. So 2a and 2a. This will help you prevent from making mistakes in your simplification. So I have parentheses around this 2a. I have 2a squared, and that becomes 4a squared. And then 3 times 2a becomes 6a minus 2, and that would be our answer. That is as simplified as it can get. Now in the next example, we have f of a plus 2. Now we have 2 terms. This is called a binomial that's being plugged in. So same process. I'm going to set up my f of x, but replacing x with parentheses. Now, one of the mistakes I sometimes see students make is they'll put an x in front. You're not putting an x in front. You are replacing x with parentheses. And then we're going to plug in the inside part, so that a plus 2. All right, so here we have a plus 2 squared, and sometimes I'll see students just distribute that square. That's not what we can do here. You either need to FOIL or you can use what I use, and that's the box method for multiplying polynomials. And that would give you a squared, 2a, and 2a, and 4. Combining like terms there, that gives us a squared plus 4a plus 4. And then distributing my 3, I have 3a plus 6 minus 2. And now I just need to combine like terms. So I have a squared, I have a 4a and a 3a, and that gives me 7a. And then I have a 4, a 6, and minus 2. So that 4 plus 6 is 10, minus 2 is 8. And you can see here, I kind of have used colors to kind of code things here and show combining like terms. This can be a helpful tool to help you organize your work. And on to the next page where we're going to see another example of doing the same kind of thing. So here we have f of a minus 3b. And again, same outside function, just to write it from the previous page, we had f of x was equal to x squared plus 3x minus 2. So again, I'm writing f of x with x being replaced with parentheses. And then we're plugging in this a minus 3b. So a minus 3b, a minus 3b. And again, when I square that, I can either use FOIL or the box method like I just demonstrated. I'll go ahead and demonstrate it again. As the class progresses, when we get into further and further videos, I will not always show the work for the box method, but you can always come back and see examples here. So I have a squared minus 3ab minus 3ab, and again, this is the multiplying step. So a times a, and then a times negative 3b, a times negative 3b, and negative 3b times negative 3b will give me 9b squared. So combining like terms there, I have, let's be consistent with my colors here, a squared minus 6ab plus 9b squared. And then distributing my 3, I end up with 3a minus 9b minus 2. Now, in this next step is where we would combine like terms, but notice I don't actually have any like terms. I have an a squared here, but I have no other terms with a squared. I have a term here with ab, but I don't have any other terms that have both ab. Here I have b squared, no other terms with b squared. Just an A, no other terms of just an A, B, no other terms of just a B, and no other terms with just the number. So this big long expression here is actually my answer. Now into this next example, we have a function here or an expression here that is called the difference quotient. When you get to Calc 1, this is probably a skill you'll use the first week, maybe even the second week, and you'll be using it with the concept of limits. For our purposes, we are just going to find the difference quotient and leave it at that. Now, a helpful thing to do if you are working with some function f of x, and again, we're using this same f of x that I wrote at the top of the page here, I suggest finding these two pieces kind of off to the side and then using them to plug in. Now, finding f of a is a little bit easier. All we're doing is just replacing x with a. So that becomes a squared plus 3a minus 2. Finding f of a plus h, I'm plugging in that a plus h to everywhere I have an x. Try and squeeze that in there. Let me zoom out a tad here. All right, and then I'm not going to show my box method here or any of my work. I'm going to just go ahead and do the box method and distribute the 3. So I end up with a squared plus 2ah plus h squared plus 3a plus 3h minus 2. And if you're unsure how I got this piece here, just pause the video, go ahead and do the box method for this, and you'll see where that came from. Now, I don't have any like terms again, but what I'm interested in finding is actually the difference quotient here. So f of a plus h minus f of a all over h. And what I have then is f of a plus h. Well, we just found that. That's this piece over here. I'm going to go ahead and copy all those terms over. A squared plus 2ah plus h squared plus 3a plus 3h minus 2. And then we're subtracting f of a, and you're going to want to put parentheses around this whole thing. F of a is this top piece here, a squared plus 3a minus 2. And then we have h on the bottom. Now, hopefully you're noticing here that there are some terms that are going to cancel out. When I distribute that minus sign, I end up with negative a squared. Well, negative a squared and positive a squared will cancel. When I distribute this negative to the 3a, that becomes negative 3a and a positive 3a, and those will also cancel. And when I distribute the negative to the 2, that becomes a positive 2. Positive 2 and negative 2 also cancel. So let's simplify what we have so far. I have 2ah plus h squared plus 3h all over h. Well, all three of these terms have an h, so I can go ahead and factor out an h. 2a plus h plus 3 all over h, and I see that my h's cancel. It has to cancel out of all of the terms on top. If only two terms had an h, we would not be able to reduce an h out. So the answer, or my difference quotient, is 2a plus h plus 3. And again, in calculus, you'll do more with what you get as your answer. All right, we have another example here, and we're looking at now f of x, and we have negative 2 over x plus 3. Now, evaluating these first couple are actually going to be quite easier than the one we just went through, the quadratic function we just looked at, but the difference quotient will be a little bit more work. So the first couple will fly through pretty quickly here. Plugging in 2a for x, I have negative 2 over 2a being plugged in plus 3, and that's just negative 2 over 2a plus 3. If this was an even number here, maybe 4, I could reduce this, but since there's not a common factor among all three terms, that is what we're left with. Plugging in a plus 2, I have negative 2 over a plus 2 plus 3. I can combine like terms. I don't really need those parentheses there. I have a plus 5, and that would be my answer. And then this last one, plugging in a minus 3b, I have negative 2 over a minus 3b plus 3. And there's no like terms. There's nothing being applied to those parentheses. So I just have a minus 3b plus 3. So those were pretty quick. There's not a whole lot we can do to simplify or multiply anything. They move pretty quickly. The difference quotient is a little bit more work, and I think when I did the formatting for this, I meant to have this vertical line test part be on the next page, but unfortunately it's not. So we're going to be a little bit tight for space here. We may have to bring some of our work down below where it says vertical line test. So here I have, again, finding the difference quotient. So off to the side again, I can go ahead and find f of a, which is going to be negative 2 over a plus 3. And then f of a plus h will be negative 2 over a plus h plus 3. And so we can see that we do not have a common denominator. Now, when we're working with a rational function, we're going to need to have a common denominator. Sometimes what I'll see students try to do is just plus h and plus h. We can't do that. We have to multiply by something, not add something on top and bottom. So finding my difference quotient, I'm going to go ahead and put my f of a plus h, which is negative 2 over a plus h plus 3, minus negative 2 over a plus 3. And then this whole thing is over h. Now, sometimes students will get confused or this looks intimidating because what we have here is what's called a complex fraction. We have fractions inside of a fraction. Well, dividing by h is the same thing as multiplying by 1 over h. So if you want to change this so that it's 1 over h times the rest of it, we can do that. Now, in order to add these fractions together, I need a common denominator. So I'm going to have to multiply the second fraction by a plus h plus 3 over a plus h plus 3. And then this first fraction will have to get multiplied by a plus 3 over a plus 3. And that will give me this common denominator of a plus 3 times a plus h plus 3. So my common denominator, what I'm working with now is what's going to go right here, is going to have a plus 3 times a plus h plus 3. And I don't need to multiply that out. In fact, it'll be better if we just leave it in factored form. And then on top, I will have my negative 2 times a plus 3. So negative 2, if I distribute that onto both of these terms, I end up with negative 2a minus 6. And then over here, I have a few things happening. I have this negative times this negative, so that will become a positive 2. And then positive 2 distributed to all three of these terms. So positive 2 times a times h and times 3. So I have plus 2a plus 2h and plus 6. And hopefully you're seeing kind of where we're headed with this in that we have a number of things that cancel again. So I have a negative 2a and a positive 2a that cancel. I have a negative 6 and a positive 6 that cancel. And what I'm left with now is 2h over a plus 3 and then a plus h plus 3. But I also have this other 1 over h over here that I don't want to lose track of. So simplifying here, I have 1 over h times 2h over a plus 3 times a plus h plus 3. Now I'm noticing here that I have an h on top and an h on bottom that can go ahead and cancel. And that is the last step here. My difference quotient is just left as 2 over a plus 3 times a plus h plus 3. And again, in calculus, you'll take that a step further and kind of talk more about what to do from there, but that's where we will stop in finding the difference quotient. And we were able to fit it in that space. So I'm going to go ahead and pause this video here, and we'll continue with the vertical line test in part 2.